In this video, we want to start to take a look at example number 3 and ask a very important question. What if it's the case that sigma, a smooth surface, is not given by something that's parametrically defined, but it's instead given by a standard z equals stuff with x and y kind of a formula? That is, it's given by some sort of a function. Now, this is kind of a tricky thing. We want to make sure that we can do this in as little work as possible. Obviously, one thing that we could try to do is to say that if I have this formula for sigma, I could try to parameterize it like we did in the previous videos. I could try to parameterize it and then easily convert this surface integral into one with u's and v's. But what if I don't have to do that? What if it's the case that when I start with a nice function, z equals something, I have a nice alternative way to set up this integral? That might be nice to know and could save me the work of finding parameterizations for surfaces, which of course can sometimes be a little bit difficult. So I'll go ahead and just note the following. So I'll say quickly that we can note that if I was to parameterize, I could say that a parameterization for sigma is actually going to be super easy to find here. If I wanted to create a parameterization, I can, but we'll see why I said we're going to attempt to skip this step in the future. But here's a way I could easily create a parameterization. Notice that if I let x just be the value of u, and I let y be the value of v, then it's super easy to find the value of z. I would just plug in the value of u, plug in the value of v, and this formula of g should compute the value of z. Right? So this works out really, really well. Of course, my bounds here would have to be given by, well, x's and y's have to exist within this particular region here. And so I would have to say that my x and y satisfy this, and so my u and v have to satisfy this as well. Now, of course, if I was to go ahead and use what we've seen in the past several examples, we could then go ahead and rewrite our integral in the following way. So if I have this integral here, and I wanted to go ahead and re-express it, I would have to say, all right, so the first thing I would do is I'd have to redefine this as working over some region D. I would then have to say that I'm going to have to change out my function f, which I'm going to have to say put in values for x, but notice those are just going to be values for x themselves, right? U and x are the same thing. My y value is v, or also just y, same thing. But my z value is now given by this formula, g of x, y. I can also say that it's the case that I would kind of have to do this magnitude of the cross product. And here I'm going to write this in terms of partial with respect to x, because again, u and x are equivalent, and partial with respect to y, because again, y and v are equivalent. At the end here, I'll just be able to say dA. The reason, though, I'm writing everything here in terms of x's and y's as opposed to u's and v's is because then I can actually use the region D, which is measured on x and y values. So once I have this, I could easily notice how I could begin to update this by using finding this cross product. So let's take a look at what we actually have here. Again, if I imagine that up here, my u is playing the role of x, this is playing the role of y, and over here I really just have g of xy, then it's really easy to see that if I wanted to, I could imagine this instead as an r of x comma y, right? Just like change up the variables and what they're called. And so I could easily see that if I wanted to go ahead and compute my rx cross my ry, that could be easily done. I could see that partial with respect to x would be 1, 0, and then whatever the partial derivative of this crazy formula g is with respect to x. I would get something very similar when I do my partials with respect to y. And again, I'll put up here my I, my j, and my k. Once I have this, if I compute this cross product, let's see, I'm going to get a negative partial derivative of g with respect to x, I'm going to get a negative partial with respect to y of g. And I'm finally going to end up with a final value of, it looks like 1. So here's my cross product. And so the magnitude of the cross product could then easily be included when I go ahead and I convert my integral all the way down. So let's see. My integral, which was d of f of x, y, g of x, y, which is supposed to be getting multiplied by the magnitude of this cross product. Well, oops, the magnitude of my cross product here, dA, this of course could be redefined now as, oops, not a z there, we have our g of xy, but the magnitude of my cross product again is going to have this giant radical, and I'm going to have my g of x, or g with respect to x, partial of g with respect to x of xy, and then my partial of g with respect to y of xy squared plus the value of a 1. And what I have then is that all of this can be multiplied by dA. Now, if I look at this, what we've seen is that there's something interesting happening here. By first thinking about this as a parameterization, that is, by thinking about parameterizing my surface, we were able to see that that's easily able to be done, and then using what we saw in the previous definition, we made our conversion. However, it was an easy enough parameterization that I could actually rewrite it all in terms of x's and y's. And if I look at what I have here, this now is an integral that still is a surface integral, but notice how easy it would be to fill in. Let's suppose, for the sake of argument, that I had a function. I had an x and a y. I could just plug in my x and y into this original formula up here. In place of z, I just plug in my z formula. And then over here, I can easily find all of these values based on the initial red function, and I would never need to find a parameterization. So this is a really, really powerful tool and technique that we can use, and I'll summarize it on the next page. So this most recent example ultimately justifies the following. If sigma is a smooth surface that's given by some sort of a function z, then it's the case that we could state a couple things. One, a normal vector to that surface is given by this here. Notice that was my cross product that we had established up above. So that would create a normal vector. But it's then also the case that I can go ahead and just write this down as a conversion of the surface integral. Don't be alarmed here by the partials. Notice that this is the same thing as saying my partial with respect to x of g being squared, because again, z and g are the exact same thing. So this is something that's very important for us to keep in mind and keep our eyes out for. There's going to be a big distinction that we're going to draw between when we're given a surface parametrically and when we're given a surface that's based on just a simple function. If we're given a surface parametrically, we want to take this old approach that we had kind of seen in a lot of the previous examples. But if we're given a surface that's in this new simple function form, we can simply use this approach, so we can avoid finding a parameterization. As you practice these ideas using the worksheets and textbook problems, I'd ask you to keep your eyes open for this. When do you need to find a parameterization, and when are you simply just given a function z equals that you can just immediately skip all of that and jump right to something like what we've seen here in the formulas?